Hi. Today we look at how to connect a small microcontroller, such as the Arduino, to a personal computer for the first time. Here we have three examples. The two on the left are called the Uno and the one on the right is the Nano. These are circuit boards designed by Arduino that have on-board microcontrollers. Here you can see the microcontrollers. The circuit boards also hold other components such as USB sockets, USB to serial converter chips, power sockets, and pins, voltage regulators, and input-output pins. There are many different types of microcontroller boards available. Ones with Atmel MCs can be programmed using the same software as shown in this tutorial, but they may require additional steps or drivers to be installed to match them. Look for appropriate support websites for help. Each of these boards use a different USB connector type, so you will need to make sure you have a good quality cable to match the socket on your board. The first one here has an old-style USB Type B. It plugs in here at the top. The next board has a smaller micro B-type connector. It plugs in here, and it a little more fiddly. And the smallest board here on the right uses the USB Mini B-type connector. For the rest of this video, I will continue with the B-type, but they should all work equally as well if you have the matching cable. Now we need to set up the computer. Okay, we're on our computer. Using a browser of your choice, search for Arduino. Here we have the Arduino homepage. If you would like to support the work they do, you can make a donation, but they will allow you to download and install the software for free. Click on Software. Here is the download page. Make sure you select the correct version for your operating systems. For example, Windows or Mac OS. If you click on this option, it takes you to the Windows app version. In various online forums it suggests this version may not be the most flexible. I will actually click back and choose this Windows 7 or newer link up here. I will click Just Download now to download it for free. It downloads. Currently, it is 113 megabytes. Once it is fully downloaded, click on it to launch the installer. We will click through these options, choosing to install all elements such as drivers and desktop shortcut. I'd recommend installing at the default file location as this may help in the future if installing additional files. Now we watch it install. Towards the end some pop-ups show up asking if we want to install the USB drivers. We will install all of them by clicking Install. And it is complete. You can now either launch the software by finding Arduino in the Start menu, or by clicking the shortcut on the desktop. When it opens for the first time, you will get a firewall pop-up. You should click Allow as the software needs to connect to the Internet to download libraries and other supporting files in the future. That's the next step complete. We have the Arduino Sketch software installed and the software has launched into a blank program. Now we can connect our Arduino to the USB port on the PC. If your Arduino is a genuine board, the software will automatically recognize it and load the matching drivers. If it is a cloned version or another type of board, you may need to install a different USB driver. You can check in your device manager to see if the driver needs to be installed. For this type of board shown, we need to find the matching driver for this chip. We can see it says CH340 on. A quick search online finds a few pages with a download link. Simply download the correct version for your operating system. This SparkFun website contains the links to the driver we require. Scroll down until you find the links for the file download. Here it is. When we click it we get redirected to another site that holds the file. It's good to get it through a well-known site so that you don't download a dodgy file. Once you have the driver zip downloaded, you may need to extract it to a new file. Here I just name it CH340 driver. We can now either use the driver installer or navigate to the driver location using the device manager to add the driver manually. From the device manager list, we right-click on the device and select Update Driver. Then we choose to browse for the driver location, and select the folder we unzipped the drivers to. Just remember, if you used an officially Arduino, you can skip this step. If your device is not official, or not seen by the Arduino software, you need to find and install the correct driver. We can clearly see the device is connected under ports in the device manager. Now we can return to the software. If you installed the drivers since inserting the USB cable, you may need to unplug it and plug it back in for the software to see it. Now we can click on the Tools tab in the Arduino software and go down to Ports. Here we need to select which port our Arduino board is connected to. It's never normally COM1. So if you can only see COM1 shows, it is unlikely to be your board. Check your connections and drivers, until you see the board connected as another COM number. Next, in the Tools tab, we will click on Board and make sure we have the correct board selected. In this video, I'm using the Uno clone, but you might be using a different version. Make sure the setting match. As you can see, there are many board versions. You can even download and add setting for many more different designs. We are now going to open an example code. Luckily, the software comes with a wide range of example codes. We can use these to start many different projects. The first example we will look at is called Basic Blink. Click on File tab, then Examples, Basic, and Blink. A new window opens. You can close the old window if you like. This is our first code. We will upload this code to our microcontroller board to make sure we have the computer set up correctly, and that the circuit board works correctly. But first, let's explain the code. The text shown in light gray is called comments. These are not part of the code and supporting notes to help us remember what is going on in the program. Comments are created either as a paragraph, between / and */, or using double forward slashes. To make the code a little simpler to understand, I will delete these comments that detail the original creators and modifiers and tell us the code is public domain. I will delete all the comments after the double forward slashes as well, including the slashes. We will add our own. If the text is too small, you can make it bigger. To enlarge it, press the Control key and plus key at the same time. To reduce its size, it's Control and the minus key. You can also go into the Preferences by clicking File, then Preferences. You can manually enter the font size here. In this example, we can see the text LED built-in. Many board versions include a built-in LED for testing purposes. On the Uno version, this LED is connected to pin 13 of the microcontroller. I personally feel it's better to refer to this built-in LED as something else. To do this, we will delete the 3 references of it and replace it with the text LED. Notice the use of the capital L and small e and d. This is important as the Arduino software is case-sensitive. Now the program does not know which pin LED is, so we will use an int, and call it LED and give it the value 13. Basically, the software will now replace all references of LED to the number 13. It makes it easier for us to name the microcontroller pins as text-based names instead of numbers, but either will work. We should also add some comments explaining what is happening to each line of code using double forward slashes. This first line of code creates a variable called LED and makes its value 13. Now everywhere we have used the text LED, it will in fact be replaced with the number 13. This is actually the pin number that our built-in LED is wired to. All programs have a void setup. This is an area where code is only executed once. This is done when the microcontroller is powered up or reset. Once it is running, the code within the void setup curly brackets will not be run again. The code seen here simply makes LED or pin 13 function as an output pin. If we needed it to act as an input pin, we could simply replace output with input, but our LED would no longer work. There is another area of the program here called void loop. Once the microcontroller is running, the code between the curly brackets is run repeatedly forever. Here we see that the command digital write is used to set LED, which is pin 13, to high. High is the same as on. On this board version, on is 5 volts. Note that not all boards work with 5 volts logic. Some may be 3.3 volts, for example. Next we see a delay command. The number within the brackets is milliseconds. Therefore 1000 milliseconds is 1 second. The delay causes the microcontroller to pause for 1 second. Then we use digital write low to set LED pin 13 to off, which is 0 volts. Another delay is used of 1 second. At this point, the code loops back to the first line of code within the void loop area, within the curly brackets. Code in the void loop runs in a loop forever, or as long as the microcontroller is powered. This code should flash our LED on and off at a 1 second on period followed by a 1 second off period. But first, we need to upload it to the chip. There are 2 round buttons at the top, one with a tick, the other an arrow. Clicking the tick button will process your code and check it for errors. It must be error-free. Any small changes in font or symbols incorrectly placed will result in an error in the lower box. As we click the tick or verify button, the green bar on the bottom right shows progress. If you receive an error, you need to use the clues provided to find the problems. Here the issue is a missing semicolon. Putting the missing semicolon back allows the code to be verified without errors. We can see down here how much program and RAM memory have been used. So far just 936 bytes of program memory and 9 bytes of 2048 RAM memory are used. If you use too much, your microcontroller will fail to function correctly. Keep it below 80% if using many variables. OK. Let's press the arrow button. This should upload the program to the microcontroller. The bar should fill to show status. If you look at the circuit board, you should see 2 small LEDs labeled RX and TX. These show the data flow on the USB receive and transmit wires. If your program upload is successful, you should see these LEDs light up for a second or more. If they do not light up, or flash very briefly, your program may not have uploaded. You will need to check your settings. For example, COM port, or board type set wrong. Your programmer settings should work as shown here. You should now change these 1000 millisecond values. You can change them to any value, but if the value is too low, our eyes may not be able to register the LED turning on or off. Experiment to see what the shortage flash period is that you can see. Here I change the values to 200 on and 700 off. Let's upload it. We can see the LED now flashes at a different rate. While this is a very complicated circuit to flash and LED on and off, it is very easy to modify it once it's all set up. We can also easily change the microcontroller hardware, and as long as it's compatible, use the same code. All we need to do is select the correct board version. This example has 3 different options for the hardware chip used. If you are not sure, you may need to look at the chips used closely, or just try the different options until one successfully uploads to the board. That's it for this video. In the next tutorial, we will look at how to connect different LEDs to the ports on the board. Thanks for watching and hit that subscribe button to see the latest videos.